Not recording. Now it's recording. Well, welcome back. I've suddenly had the courage to go through with recording the rest of the videos, which is a good job on me. Now let's look at the t-test for independent means. Logic is distribution of differences. The t-test for independent means is a statistical method used to compare the scores of two completely separate groups. This test is highly common in psychological research, such as comparing an experimental group against a control group, or comparing males, alpha males to be exact, versus females. Now, of course, individuals in one group are entirely different from those in the other group. This is a prerequisite that you have to meet. There is absolutely no overlap. The same person does not belong to both groups, meaning the scores of each group are independent of each other. Therefore, independent. What? He said this thing. And of course, we don't know the variances. True population variances are unknown. However, we have to assume that the variances between the samples are actually roughly the same or generally treated as the same. I didn't double check that, but if I remember correctly, that should be the case. So group 1 is the experimental group, group 2 is the control group, entirely different, unknown variances, and what is this? Anyway, so the logic is distribution of differences. Since the groups are independent, there are no natural pairs of scores, so we cannot compute direct difference scores. This is in reference to the dependent means testing for individuals. Instead, the focus is on the difference between the means of the two groups, which is M1 minus M2. The means of the two groups. The null hypothesis states that there is no difference between the two populations, so your control group and your experimental group are the exact same. Therefore, when you take their means and then you subtract them from each other or try to find the differences between them, you're going to find absolutely zero difference. And the comparison distribution is the observed value is compared to a comparison distribution, which is a distribution of differences between means. If the null hypothesis is true, the mean of the distribution of differences balances out to zero in the long run. Wow. Exactly what I said. Step-by-step calculation process. Now, I don't know how my infographics started turning into kindergarten level, but they have, and I can't really complain, really. So the first step is taking the sum of squares from the first group that you have. We're gonna call this group 1. So in the group 1, we are just running this normal variance getting operation. What is the normal variance getting operation? It's when you take the sum of squares and then you divide it by n minus 1. Of course, this is the t-test version because we don't know the universe parameters, the population parameters. They're unbeknownst to us, so we need to estimate them. So this S2 that we find, which is the variance, is actually just an estimation. And as you can see, we repeat the same process for the other group as well. So we treat each group as a separate matter at hand initially. And then we calculate the pooled variance of both of them. Now, since we said the variances of both groups are roughly the same, we're gonna make it even more, I guess, accurate by calculating the pooled variance. We're gonna add the both variances together. However, if we were to just, average them out together or, get the cross product of them, like multiply them together or something like that, it won't really give us the absolute most certain value. Therefore, we resort we resort to a weighted averaging function. So what we do is for each variance, we multiply it by the degree of freedom that we have within the scope of this. So let's say, looking at group 1, we are taking the variance within group 1, and then we are taking the degree of freedom of group 1, which is n1 minus 1, and then we are dividing the df1, which is the degree of freedom of group 1, with the total degrees of freedom that we have. So this usually amounts to what it's these two df values getting combined. It's n minus 1 plus n minus 1, basically. So if you have 10 people here and 7 people here, your df total is 17. It's as simple as that. And then we repeat the same thing on the other side as well. We're going to treat the second group as well. However, as we said, if this is 7 and this is 10, we're going to put 7 here. What this accomplishes is it kind of divides the importance of both values. So the one with the 10 is seen to be, more accurate since it has more samples to it. Whereas the one with 7 people is likely to be considered as a lesser statistic. And then we get the pooled variance as indicated by SP2. And then we go to the variance of sampling distributions. Now we have the big boy pooled variance. And then, now normally what we were doing is we were getting the variance and then we were dividing it by our sample size, by our n, and then we were getting the distribution of means variance, something like that, variance of differences. What are these terms? So in order to get to that, we are basically using our pooled variance as our normal variance, like as if we had a universal variance and we just use this pooled variance, and then we divide it by n on both sides. Again, as you can see, we have 2 separate groups. Now, something very convenient happens since the null hypothesis states that there is absolutely no difference between these two values. Then we don't really need to look at it because it will amount to 0 as well. So we're getting differences, we're getting the variances from both of these distributions and then adding them up together into SD2, which is variance of differences. Now, because, when you see difference, you automatically go to, well, it must be a subtraction. But I guess not, because when you add 2 variances together, it becomes a bigger difference, if it makes sense. Fundamentally thinking, just purely out of logic, just the plus sign works better. So now we have the variance of differences, and then we get the standard deviation of differences as usual, and then we calculate our final t-score. How we do it is by taking the first group, M1, minus M2. And then that yields us with our final t-score. Let me see if I missed anything, some squares, etc., 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 etc. Yeah, okay. Amazing. Divide the observed difference between the sample means by the standard deviation of the differences. So when we look at it in an expressive writing study, just an example, as you can see, we have an experimental group of 10 people and a control group of 10 people, and they study for 20 minutes a day for 4 days, and then one group writes their most traumatic life experiences, and then the other group just writes about whatever, nothing important really. So the outcome is then measured on a scale of 0 to 100. We can see in the first group we have M1 has amounted to 79. So the average score or the mean score that this group has yielded is 79. And their their deviation is 94.44, and then their degree of freedom is 9. So since we have these metrics already, our job is much easier. So since the df of this is 9 and the df of this is 9, we just add them together and then use it for pooled variance calculation. 18, and since this is 9, we put 9 here, and then we multiply it by the deviation inside the group. And then, of course, we repeat the same thing for the other group, and then it yields us with 102.89. And then we go into the variance of differences, which gives us the 10.29 plus 10.29. What? Something happened. Yes, something major happened. We forgot to subtract 9 from these. Now, since this is our universal variance, we need to divide it by our sample size to get per group variances. What is it? Distribution of means variance, whatever it is. So we divide it by n, which yields us with 10.29 on both sides. The reason it's the same is because the degrees of freedom on both sides are the same. Therefore, the sample sizes are the same. They're probably 10. Or not probably, they are 10, definitely. So since when you divide this by 10, you get 10.29. And of course, we get the variance of differences together, and then it's 20.58. And then we calculate our standard deviation by taking the square root of it, and that yields us with 4.54. And the last thing to do is just taking the difference between the two means, which is 79 minus 68 divided by 4.54, which yields us with 2.42. Now, of course, we consult our t-table to see what our critical value is. And then since we have decided that it was 2.101, then we can say for definitely that, yes, we can reject the null hypothesis that there was absolutely no difference between the control group and the experimental group. So let's see. We also have the effect size and power. Of course, our Cohen's d is notorious. So to calculate the Cohen's d for dependent means is you do almost the same operation as what you do for getting the final score. You take M2 out of M1, and then you divide it by the standard deviation of difference something. Now, there's a bit of misleading terminology here, because this is not actually standard deviation. It's actually standard error. We are using the standard error to get this value. But here in Cohen's d, we are basically using the standard deviation that we got from our pooling operation, which was here. So we calculate the pooled variance, and in real world, when you take the square root of this gives you your standard deviation. Whereas when you go here and then you divide it by n, etc., then this gives you your standard error. And of course, let's see anything else, study comparing. So here's an example, 12.99, and it yields a medium effect size because it's close to 0.50. Of course, to improve your statistical power, you can do a larger effect size. You can do 10 participants per group. Oh, wait. You can get more participants per group. You can go and convert your test into a one-tailed test, and you can lower or make your significance level higher. And then that will make your power higher. Now, I think that's all there is to discuss. I think you should read the professor's notes, in my opinion.